last few turns we have been discussing on the photochemistry of 1,4-diene which undergo di-pi-methane rearrangement. So the basic criteria for molecule to undergo di-pi-methane rearrangement, we should have two pi bonds separated by a methylene group, one pi bond, another pi bond separated by. Now what happens if we have a system like this? One pi bond is substituted by a carbonyl. Whether we expect under photolytic condition we expect similar type of rearrangement or not. So what happens here also, when we have a system like this, then this may also undergo, first we can expect excitation of the carbonyl to generate a 1,2 diradical, and then this as usual this diradical may generate 1,4 diradical to the attack of this radical to other double bond. Then we expect the formation of the cyclopropyl cyclopropane ring, this radical here and oxygen here. Now this will also undergo the opening of the cyclopropane ring. So we can expect either this going a double bond. Now it will be it will most probably the O dot will convert to carbonyl most and then the cleavage of this. So this is the most probable the transformation which will lead to opening of this radical, the converting of this to carbonyl once again, a diradical like this, and this will combine to give a vinyl, the carbonyl cyclopropyl group. So this is a similar rearrangement has been observed when one pi bond is substituted by a carbonyl, and this rearrangement we call is a oxa-di-pi-methane rearrangement. So this is also a very interesting rearrangement where the other product, where if we can make a double bond here and a cleavage of this may lead to a 3-membered with heteroatom. This is once again will be under strain, and then the other possibility where the carbonyl O is converted to carbonyl is more feasible. So this is a most feasible pathway, and this rearrangement is known as oxa-di-pi-methane rearrangement. Several examples have been reported by studying the different substituted carbonyl compounds, and then, so for example, when we have a system like this, C double bond O, and then this is, so this is a similar type of reaction. This is just to unsubstituted oxygen, where to show the what type of things. Here also we expect similar rearrangement, excitation of the carbonyl, and then the formation of the cyclopropyl radical, this one, and then and then this, the conversion of this to carbonyl and opening of this to give a product like this, a diradical species, and then this will combine to give. So we can see it is only the exclusive product is formed, and although the cyclopropane ring is highly substituted, and then so we have a di-pi-methane rearrangement, we have oxa-di-pi-methane rearrangement if one of the pi bond is substituted by a carbonyl. The other examples which are reported in the oxa-di-pi-methane rearrangement, you can see here, this is a of course it is not an oxa, but the and same as if the pi bond is substituted by a C double bond N, then what happens? So if we have a system like this, N C double bond O, and then of course so you have one pi bond, another pi bond is, we have not a C double bond C, but we have a C double bond N. So this under photolytic condition we expect a similar rearrangement like this N dot and then the CH2 radical again. So here this will there is a possibility of the converting this double bond and cleaving of this. Then in that case we are going to generate a product like this, where the nitrogen is a part of the ring. So in fact the nitrogen itself, I mean 3-membered itself, is under strain, and presence of an hetero atom in the 3-membered ring makes more unstable and more under strain, and hence there is other possibility. Conversion of this to C double bond N and opening of this is more feasible, and then this will lead to a C double bond N, the radical like this, and then this will combine to give a a product like this. So this is another so this is really you can see that is a highly generalized reaction, the di-pi-methane rearrangement, when the two pi bonds is a part of the carbon system. Oxa-di-pi-methane rearrangement, where one of the pi bond is a part of the carbonyl. Aza-di-pi-methane rearrangement, where one of the double bond is a part of the C double bond N. So we have also all 3 different type of rearrangement which are available. In all the cases is the open chain system is generated so different examples have been reported, and there is another example here. We have a C double bond N. So we have a system like this where C double bond N, there is a substituent. This is again we have a double bond. This is a, and then this is different substituent. So this, as usual, in the presence of light, we have a 2 pi bond separated by a methylene group, 1 pi bond, another pi bond separated by a methylene group. Is nicely set for di-pi-methane rearrangement. Aza di-pi-methane rearrangement, and then we first, of course, excitation of one of the double bond, and then the formation of the the 1,4 diradical, this one, and this is more feasible, and then the conversion of the 1,4 diradical, opening of the cyclopropane ring. This is a newly bond form, and then the other bond cleaves to give this, and then a diradical like this, and then this will combine to give a similar product have been reported through the formation of this. So you can see we have all 3 different types of reaction. The di-pi-methane rearrangement, oxa-di-pi-methane rearrangement, and aza-di-pi-methane rearrangement. Whether if 1 pi bond is a part of a carbon system, other part is a part of the carbonyl, whereas the other part is a part of a now coming to the next one, so even in the di-pi-methane rearrangement observed in the case of berylline. So for example, we have a system like this. This is a common name for this is berylline, or is nothing but is a bicyclic system. Is a ring junction between 1 and 4. So if I write in a more conventional method, it looks like this. Is a bicyclo 222. This is berylline is a common name. Otherwise, it is bicyclo 222. Means the number of carbon on the right side, number of carbon on the left side between between the ring junction, and number of carbon between the ring junction. So 222 bicyclo, 222 cyclo, octatriene, because octa is the number of carbon, 2468. 8 carbon, triene is the 3 carbon system. So this is the name for this particular molecule, and common name is berylline. And if we look this molecule very carefully, it is a, I'll just rewrite again. So it is a, this one. In fact, we have already discussed this, but this what I want to emphasize from here is this: if we take any two double bonds, we take this double bond, if we take this double bond, so these two are separated by a methylene group. One pi bond and another pi bond separated by a methylene group. So this is nicely set for under photolytic condition. In the photolytic condition, this is nicely. So if we take instead of this, if we take these two double bonds, one double bond and another double bond is separated by a this again this one, and then separated by methylene. So we take any of these two double bonds, it is both two double bonds are two pi bonds are separated by methylene group. So it is nicely set for di-pi-methylene group. So it is nicely set for di-pi-methane rearrangement. Di-pi-methane rearrangement. People have tried cyclic system because earlier what we have seen that an open chain is going to give you a 3-membered ring. If we take a monocyclic system, it generates a bicyclic system with the construction of 3-membered ring, and that was the main aim to see how this reaction. So if we take these two double bond, this one, and then under irradiation and excitation of one of the double bond, either this or this, contain a dialectical species cyclopropane. The main intermediate will look like this. There is a right. These intermediate through the, so this is the new bond formation, is a 3-membered ring, the dialectical, and this is a double bond here. This is the intermediate which is formed. If we combine, if we take these two double bonds, then we'll end up with a so we get a cyclopropane this dialectical here. So any of these and then the double bond any of these double bonds will, and now it will open opening of the cyclopropane ring. This cyclopropane ring will open up, forming a double bond. If we have to open this one, and then we end up with a so this will combine as there is a new double bond, and then this will combine, then it will looks like this. This is 3-membered ring. So this is the product. You can see that the berylline, and then if we write in a better way, it looks it is a this is the product. This is called semi-bulvelene. So berylline under photolytic condition undergo di-pi-methane rearrangement to give semi-bulvelene through the formation of one 5 bond, another 5-membered ring, and then another 3-membered ring. So 553, a tricyclic ring system. A tricyclic ring system is formed. On the on direct photolysis, it has been found that it gives undergo cyclooctatetraene. This is the product is formed on direct photolysis. Direct photolysis on cyclooctatetraene. So on the on this molecule gives a very interesting undergo di-pi-methane rearrangement to give a tricyclic system, and then this reaction has been also substituted with a benzo barrier. Say for example, instead of only one double bond, if we have a benzobarylene. So this also should also undergo in principle one pi bond and another pi bond separated methylene group, or if you take these two, one pi bond, another pi bond, separated methylene group. So this and even a dibenzobarylene, if these two double bonds are part of the benzene ring, can also undergo similar type of rearrangement. So it's a benzobarylene, this is a dibenzo. So this is dibenzo, one benzene ring, another benzene ring, and this is the barylene. Dibenzobarylene and benzobarylene also undergo similar type of rearrangement. If you write the steps involved in this, so you can just write like this: by just combining these two, by involving these two double bonds, then we can think of an intermediate like this. And of course there is no change in this part as it is. There is a generation of a diradical here, 1,4 diradical, to the formation of the 3-membered ring. This will open up, or even this will open up, so we can cleave this, or we can cleave this. So we end up with a diradical, and then this will combine to give a product like this. Okay, so we have a right, and then this is this one, and then there is a formation of a 3-membered ring. The benzobarylene is remaining as it is. So you have a benzo semibulvarene, 3-membered ring, benzo semibulvarene, and this we can write in a better way. We can write a product. This is a formation of a 3-membered ring, is double bond, and this side is the benzo. So benzo semibulvarene, semibulvarene as the product, whereas same as this one, also incorporating one pi bond, another pi bond, or this any of these two pi bonds of the benzene ring can participate for di-pi-methane rearrangement, to give the similar type of product. So writing similar way, cyclopropyl radical, cyclopropene with a diradical, and opening of the cyclopropene. So ultimately the product which we will get after di-pi-methane rearrangement, which will look like this. Is a 3-membered ring here as a benzobarylene. Now it is dibenzobarylene, dibenzo semibulvarene, and this is benzo semibulvarene. So you can see that this reaction has been exploited. Barylene as a di-pi-methane, benzobarylene as well as dibenzobarylene has been. Now people have also looked into different substituent at bridge head carbon. Here by taking a mono substitution, say for example, if you have a dibenzobarylene with the R1 and R2 and different, first we mono substituted, say a lot of work has been done by George and co-workers. The this is a dibenzoberylene, dibenzoberylene with bridgehead substituted with uh, bridgehead substituent. So you can have an R here, different R substituent like R could be a methyl group, methoxy group, OH group, OR, of course is already nitro, NO2, cyano, and so on. So you can have a electron donating group, CHO as well, electron withdrawing group, and so on and so forth. And so just wanted to see what is the effect of these substituents on the di-pi-methane rearrangement, how these substituents are going to affect on the rearrangement of, I mean the under photolytic condition, the effect of these substituent on di-pi-methane rearrangement, because one pi bond, another pi bond substitute of methane group. So whether these substituents are going to be affected, or is going to be these two double bonds are going to be involved in this rearrangement. And this substituted dibenzoberylene can very well easily be synthesized from substituted anthracene derivative. So if we have a anthracene, you have a R here, depending all these substituents as R plus dibenzoyl acetylene, COC6H5, COC6H5. This is so 9. This is 9 and 10. This acts as a diene, and the dienophile, if we heat it or under acid catalyze, it can undergo 4 plus 2 cycloaddition reaction, or called the Diels-Harder reaction, to give the substituted anthracene. So preparation of this bridgehead substituted dibenzoberylene is very easy by just taking the corresponding anthracene derivative, and the acetylene acting as a dibenzoyl acting as a dienophile undergo 9-10 addition at 9-10 position. So this can add to and then this will, and then we can substitute. Of course, we have a COC6H5 here and COC6H5 here. So these reaction, and the Professor George at IIT Kanpur have also have been extremely involved in this, in photochemistry of these, and not only monosubstituted, even di-substituted anthracene has also been studied. Means instead of monosubstituted, di-substituted, say for example this is R1 and this is R2, and with dibenzoberylene, di-substituted 1,2-dibenzoyl dibenzoberylene, 1,2-dibenzoyl, and then this is again the photochemistry. What is the has a lot of detailed study has been done by the similar group, and at RL Trivandrum as well as in IIT Kanpur, to see the effect of this di-substituent on the formation, on the di-pi-methane rearrangement, of whether it undergoes what is the effect role of this substituent. It is found that the similar product, these products can very well obtain from taking the corresponding anthracene R1 and R2 here, R1 and R2, and then heating with dibenzoyl acetylene, COC6H5, and then when it is heated, it can also undergo. It has been found that if the substituents are bulkier, and then and then of course dienophile also has a very bulky group. So in bulkier substituent, the addition at 9-10 position is not taking place, but addition at 1,4 position, 1, 2, 3, and 4. 1,4 position, addition of this dienophile to 1,4 position taking place, and instead of the 9-10 adduct, this is a 9-10 adduct, naphthoberylene, naphthoberylene has been reported because of the steric intense between so if the naphthobalin we can write. So addition is taking place at this. So this is R1 and this is R2, and then we have a. So this and of course we have a two benzoyl group COC6H5 and then COC6H5, and this type of rearrangement. This type of product has been observed when there is a when these R1 and R2 are bulkier, and then of course due to these two double bonds become more reactive. Now the photochemistry of both dibenzoberylene with a disubstituent with a dibenzoyl alkene moiety, naphthoberylene with a disubstituent 19 position with a dibenzoyl group has also been investigated in great detail, and it has been shown that this also undergo similar type of rearrangement, and which we will discuss in the coming lectures. Thank you very much.